So what we're going to do now in this short little podcast I'm putting together here is a little waves toolbox. It's all the equations we're going to use in this unit, okay? First big equation, F equals 1 over T. What does F stand for again? Frequency, which is measured in hertz, named after the rental car company. Now, it's a German guy, okay? And T is for, anybody know? Time, but technically it's called the period, okay? The time for one cycle. And F equals 1 over T is the reciprocal of T equals 1 over F. I don't like to memorize them as two equations. They're the same idea, okay? So, for example, Mr. Lau is very talented. I can clap 5 times a second. Wow, okay? That's a frequency of 5 hertz. What would be the time for one clap? If I can clap 5 times a second, one clap is just 1 over 5, a fifth of a second, 0.2 seconds, okay? That's all. Next, equation number 2. This is a biggie. V equals, what's this upside down looking Y thingy? Lambda. That is a Greek letter for lambda. We use that for wavelength. In physics, we run out of letters, okay? There are more than 26, if you include capital 52 ideas we approach, so we got to use some Greek letters. Makes us feel cool, okay? Velocity is equal to wavelength times frequency. If you look at the unit analysis, velocity is just a fancy word for speed with direction. It's meters for wavelength. Frequency is 1 over seconds, meters per second. Another way to look at that is V equals delta x over t. That looks scary. All that is that's just old-fashioned speed equals distance over time. We just are using the nerdy physics symbols, okay? For now, it's not a big deal, but it helps to just start using the vocabulary and the symbols, okay? When we study sports physics, you'll see why delta x is better than distance, because it accounts for direction, okay? When we do our 4-step problem-solving process, these are the symbols you want to use for step 2. Because once you identify, like here's a submarine, it's underwater, it shoots out a sound wave with this velocity, it takes this long for the echo to come back, that's time, in seconds. Found out how deep the ocean is, that's delta x, bam, that's half the problem, okay? Is identifying your knowns and unknowns. Speaking of which, the 4 steps isn't to annoy, it's to help you see it, okay? So on that submarine problem, by drawing it out and breaking down your knowns and unknowns, you realize that to get the final delta x, how deep the ocean is, the sound wave goes down and back. So when you solve for the final distance to the bottom of the ocean, you just divide it by 2. Okay, so the picture helps you. If you fish a lot, you might have one of those cool sonic ranger thingies. So you can see the bottom, right, of the lake and the fish and all that. Next, I know this looks all freaky and scary. This is just the velocity of air, of sound in air, rather. So unless they tell you otherwise, you can assume that if there's a sound wave, la 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 la, or a guitar playing, that you live on which planet? We live on Earth. Welcome, we come in peace. And the last time I looked, Earth is surrounded by air. The speed of sound in air is 340 meters per second, roughly 750 miles per hour. That's Mach 1 at room temperature, 20 degrees Celsius. Otherwise, you can use the speed of sound in air equation where the temperature changes. It's 331.5 meters per second plus 0.6 T. So when we did the speed of sound lab where you snapped into a tube, if I gave you the temperature with the thermometer, you could actually calculate how fast the sound is traveling there, okay? So all it is if the air gets warmer, if you heat up air and it's hotter, the molecules move faster, then the sound wave travels what? If the air's hotter, it's going to go what? Faster, right? And if it's colder, it's going to go slower. Great example in terms of analogies, like during our homecoming pep assembly there, the senior section was nuts, wild, lots of energy, right? So if you guys started like generating a wave, it would fly through the senior section really quick. In the freshman section, they're just kind of like not moving very much, right? So that's like cold air. The molecules don't have a lot of energy, okay? Next, speed of light and radio waves, any electromagnetic radiation. All light and radio waves, they all move at the same speed, 3 times 10 to the 8th meters per second. That's 300 million meters in 1 second. That's 7.5 times around the Earth, or about 186,000 miles an hour, something like that, okay? So all it is maybe you'll notice that if you're ever at a concert, outdoor theater, and you have the cheap seats swaying back, you might see the performer on stage, or there's a jumbotron, and as they sing, it looks like they're kind of out of sync. And that's because the light gets to your eyes like instantly, and then the sound, because it only travels at 340 meters per second, 700 miles an hour, there's like, a quarter-second delay to get to you, okay? Next is this weird equation, I equals P over 4 pi r squared. What the heck is that? This is for intensity. The energy of a sound wave is equal to the power in watts over 4 pi r squared, which is square meters. So in other words, if you drop a rock in a pond, then the waves ripple out. Well, sound when you clap your hands or you make a sound, la 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 la, it travels outwards in 3D. So anyone recognize 4 pi r squared?
Yeah.
That's the equation for the surface area of a what? Of a sphere, okay? So all it is how much energy, how much power rather, the watts are radiating out from a circle in terms of square meters, how far away you are, okay? We didn't make a big deal about this equation. It's just kind of a plug and chug. I think I just gave you one homework problem. You just shove in the numbers. Here's what I want you to get out of this. Practically speaking, in real life, the only thing you ever care about is probably when you're hooking up a stereo system, okay? When you finally move out of your parents' house there, yeah? You're not going to mooch off them forever. You go off to college. So you're going to set up a system in your dorm room. What will give you better sound? A 100-watt stereo or a 200-watt stereo? Obviously. Should be a 200-watt, yet twice the energy, okay? Wattage, okay? And then the other factor is distance. So see how it's 4 pi r squared? So here's the thing I want you to realize. It's an exponential relationship. If you are twice as close, it's not twice as much energy. What's 2 squared? It'll be what? 4 times the energy. See that? So if you go to a concert and you got front row seats, yeah, and your friend has a cheap seats, they're like 10 rows back. If you're 10 times further away, it's not 10 times less energy to your ears. What's 10 squared? 10 times 10, everybody. 100. It's 100 times less intense there, okay? So the thing you got to realize is because sound travels in 3D, it's an exponential relationship, okay? Next, decibel scale. Decibel scale. We'll take questions at the end, okay? Let's just get this all covered here. Decibel scale, the technical definition of a decibel is 10 times the logarithm of the intensity of the sound divided by I0, which is 0 decibels, the threshold of hearing. 1 times 10 to the negative 12 watts per square meter. That's really technical, okay? Here's what I want you to get out of it. The decibel scale is an exponential logarithmic scale. So the rule of thumb is for every 10 decibels you go up, it's 10 times the energy. But to the human ear, it only sounds twice as loud. What's the practical thing I want you to get out of this? The practical thing is it's very easy to trash your hearing. Let's say you listen to your music 20 decibels louder than your parents, okay? So how much louder is that to the human ear? For every 10 decibels, it's a factor of 2, right? So 20 decibels would be 2 times 2. What's 2 times 2? It's 4 times, right? See that? 4 times the loudness. But how much more energy? Aha, it's going to be 100 times the energy, okay? Remember we had our screaming contest, okay? And we had, who are our 2 crazy ladies here, there, right? We had a bunch of people screaming there, okay? Oh, yes, okay, we had people screaming there. And when we had 2 people screaming, was it twice the decibels? Was it 200 decibels, 240 decibels? It wasn't, right? It was only about 3 decibels more. That's all, okay? So notice, for every 3 decibels you go up, it's about twice the energy. So 6 decibels would be 4 times, 9 decibels, 8 times. Aha, 10 decibels, 10 times the energy, okay? Finally, and then we're done, let's just get this covered, is music, okay? Music. There's only one number you need to know when it comes to music. That is the semitone ratio, the magic number, the 12th root of 2, 2 to the 1/12th power, okay, which is about 1.05946. Because in order to double your frequency in octave in 12 steps, the 12th root of 2 is the only number you can multiply by itself 12 times to double your frequency, okay? And you know what? This one is so weird. I'm just going to review this really quick by doing a quick example problem, okay? So how about, let's say I tell you that in A4, let's do this from scratch here, okay? A4 is right here. This is what a orchestra tunes to right here. In A4 is 440 hertz. And I think if you're in the orchestra, in the old days, the honor went to the oboe. The oboe got to play do, re, mi, fa, sol, la, la. They had to play an A4, and then everyone tuned to that. Now it's all electronic tuners, okay? Now let's say we want to pick a different note. Let's say we want to do a B4, okay? How do you go from an A4 to a B4? Common sense. Are you going up the scale or down the scale? You're going up the scale. And in fact, what you got to do is, and this is the only tricky thing, you actually should draw out a keyboard unless you know music, okay? You have to go from an A to an A sharp to a B, okay? You have to climb 2 half steps, okay? So all I got to do is I take 440 as an example. If you want to write this down, that's cool. And then you multiply by, what's that magic number? 2 to the what? This is nuts, right? 2 to the 1/12th power. It's the 12th root of 2. Got it? Not square root, 12th root. And then, did I put in 1/2? I was seeing if you were paying attention. There you go. It's called food coma right after lunch. And still getting over my cold there. Thank you. 2 to the 1/12th power. Every once in a while, Mr. Lau deliberately makes calculator errors to see if you're paying attention. As a service to you to help you focus. Just kidding, okay? 2 to the 112th power. But I'm not just taking one step up to go from an A to an A sharp. If I want to get to the B4, I have to go up how many steps? 2, right? So I have to multiply by the 12th root of 2 twice. So the easy way to do that is I can then just put this in parentheses. There we go. And then I'm going to raise that to the second power then. So I'm multiplying it by 2 to the 112th power twice. Okay? So it ends up being 2 to the 212th, something. Don't worry about that. Just let the calculator do that. So in the end, it's 493.88 hertz. Using common sense, does that make sense? Did we go up? Yeah, we went up 2 half steps, or that's called a whole step. How about let's try the other way? Instead of going to an A4, why don't we go down? What do you guys want to go down to? How about go to, instead of a G4, want to go to an F? Okay, so how do you get to an F from an A4? If we go to an F, we would first go to A flat, that's 1, to a G. There's the bell, there we go. A flat, lunchtime for some people, there we go. So 1, 2, 3, 4. We're going down 4 half steps. You guys see that? Everyone okay with that? Going down the scale there. By the way, if you don't have musical training, you're at a little disadvantage. That's okay. Just draw out a piano keyboard, that's all, on your note card, okay? So instead of multiplying by the 12th root of 2, now I'm going to divide, okay? That's the trick. I'm going to divide by 2 to the 1/12th power, but how many steps do we have to go down? I'm doing that again. Coordination. Yeah, we're going down 4 half steps. So you want to raise that to the 4th power, okay? Because we're going down 4 steps. You see that? And we get 349 point whatever, 228 hertz. So using common sense, does that make sense that it's a lower frequency? It does. We went down. Okay? So what I was trying to do for you guys is to put together in a nutshell the key equations for this unit. Okay? We learned a lot about basic properties of waves and also sound and acoustics and the loudness of the bell. Ha! You know, our bell's not too bad. It's around, I think, 90 decibels or so, but the fire alarm is so annoying when it goes off, yeah? It's right at 120 decibels, the threshold of pain. And I'm thinking Friday, when we have our assembly at the end of the day, it's going to get loud and crazy, okay? Maybe 122 decibels. So anyhow, in a nutshell, these are our toolbox of equations we're going to use. Just like a carpenter needs hammers and screwdrivers and drills and whatever, this is what you need to attack wave and sound problems.